Good afternoon all. Welcome for the next point of boundary layer theory. In the last lecture we have seen what is meant by displacement thickness. Now move forward for the momentum thickness. Let's have the definition. Momentum thickness is defined as the distance measured perpendicular to the boundary of a body by which the boundary should be displaced to compensate for the reduction in the momentum of flowing fluid on the account of boundary layer formation. So if you compare both the definitions, displacement thickness and momentum thickness, everything is same. Only difference is that compensate for reduction in momentum. In previous there was a, instead of momentum, a discharge or flow rate. So let's see what is meant by this. It is denoted by theta. Consider the flow over a plate as shown in the figure. Fluid is flowing in this direction. There is one stationary plate and boundary layer is formed. We have considered this section which is at a distance of x from the leading edge. This is the leading edge. Take the elementary strip at distance y from the plate having thickness dy. Same thing which we have done previously. This distance is x and there is one strip which has thickness of dy and it is situated at distance y from the plate. The mass of fluid flowing per second through that elementary strip is given by the equation rho u b dy. Rho is the density, u is the velocity at distance y, b is the width of plate and dy is the thickness. B into dy is the area, u is the velocity, area into velocity, discharge multiplied by rho is the mass of fluid flowing per second. How to calculate the momentum? Momentum is nothing but mass into velocity. So mass flow rate multiplied by u, you will get the momentum of the momentum of fluid in the absence of boundary layer. Remember previous derivation. In that also we did the same. If suppose there is no plate, when there is no plate, same amount of mass we have to consider and velocity u will be there. So check it carefully. Here small u is used because we have to consider same mass. Whatever mass is here, same mass we have to consider here, and that mass multiplied by u, capital U is nothing but streamline velocity, means which is original velocity. If plate will not be there, everywhere this velocity will be present. Only in the flow there is this small strip present, and through that small strip this much of mass is flowing. In the exam most of the time you are making the mistake for this small u. Here small u is there because to maintain the same mass. If you put this capital U here, the mass will be different as compared to the mass we have seen previously. Loss of momentum through the elemental strip, rho u b dy into capital U, which is more, this momentum is more, this momentum is less. So taking the common things out, rho b u are common, into the bracket capital U minus small u into dy. Then total loss of momentum per second through BC will be equal to integration 0 to delta rho bu into bracket u capital U minus small u d. Let the theta distance by which plate is displayed when fluid is flowing with a constant velocity u. Again, here we are considering there is a plate as well as fluid flowing over the plate is idle fluid. When idle fluid is there, means this is the condition. Plate is there, fluid flowing will have u velocity and idle fluid is there. Due to that idle fluid, if we consider our previous section, in this section, everywhere there will be constant velocity. No boundary layer will be formed. So we have to compensate the momentum. Here in this case, momentum will be more. So we have to make same momentum as we have seen in the previous case. For that, we have to shift this plate by distance of theta, and we have to calculate the loss of momentum when we lift the plate to distance theta. Means we have to find out what will be the momentum is present through this section. This section we have to consider. So how we are calculating the momentum? Rho is the density, area into velocity multiplied by velocity. Here rho is the density constant, theta is the height, width is b, and now velocity is everywhere capital U. This whole bracket multiplied by u, as we have only one velocity present. So it will come rho theta b u square. So this will be the momentum which is lost when plate is shifted. If plate will not be shifted, then this will be not there. Now we can equate. This equation is the loss when we are having plate as well as idle fluid and we have shifted it by distance theta. This we have seen in previous equation. When we equate both and make more simplification, we will get the value of theta, which is equal to g integration 0 to delta small u by capital U into bracket 1 minus small u by capital U bracket complete dy. So this equation is the final equation. There is one concept which is called as a shape factor. Shape factor is nothing but displacement thickness divided by momentum thickness. This term you should remember. I hope you have understood little bit the concept of momentum. This equation is much similar to previous one. Now we will move for the next point, energy thickness, delta double star. The definition of energy thickness is also same. It is defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for the reduction in kinetic energy of a flowing fluid on account of boundary layer formation. The word new come here is the kinetic energy. In previous equation there was a momentum. Now instead of momentum, kinetic energy is present. Let's see the derivation. It is denoted by delta double star. Consider the flow over the plate as shown in the figure, having section at a distance x from the leading edge. Here is the plate and this is the section which we are considering. This is the velocity profile. There is a small strip. This is the small strip. This strip is having thickness delta y, which is situated at a distance of y from the plate. The mass of fluid flowing per second through the elementary strip of thickness dy at the distance y from the plate is given by same equation, rho u b dy. Mass is remaining same. Through this strip, this much amount of mass is flowing. Now we have to calculate the kinetic energy. Kinetic energy is nothing but 1/2 mass per unit time multiplied by velocity square, velocity at the strip square. So 1/2 rho into mass into velocity, this is the mass flow rate multiplied by u square. Then similarly we have to consider the condition when there is a no plate. If plate will not be there, this much amount of mass multiplied by 1/2 multiplied by, consider here instead of u, capital U square will be. So 1/2 mass per unit time velocity at strip when plate is absent and bracket square. So equation will be 1/2 into bracket rho into dy into b into u multiplied by capital U square. Now see the difference, same. Instead of small u, capital U will be there, but this u is remaining same, small u, because we have to maintain the same mass. This mass and this mass will be same. Mass is remaining same, only velocity is changing, and this kinetic energy will be more as compared to this kinetic energy. Hence, reduction in kinetic energy of a fluid per unit time through the strip due to insertion of the plate is this equation 2 minus equation 1. So 1/2, and this is equation 2, this is equation 1. So you will get 1/2 rho dy bu multiplied by into bracket u capital U square minus small u square. Rearranging the terms, we will get final third equation. Then total reduction of kinetic energy of a fluid per unit time for whole boundary layer will be the integration. Integration 0 to delta 1/2 rho into b into u multiplied by capital U square minus small u square into dy. This will be the equation number. Then as usual, now we are considering that there is a plate, but over that plate idle fluid is flowing, and due to that idle fluid there will not be creation of a boundary layer, so kinetic energy will be more. Then we have to shift the plate by distance of in such a way that kinetic energy in first case, like plate is there, real fluid is flowing, will be equal to kinetic energy of a plate having kinetic energy of plate having idle fluid. Means we are considering same way, there is a plate but idle fluid is flowing, and this was our previous condition. When boundary layer is formed, here boundary layer will not form, no boundary layer. Here boundary layer is formed. Due to that formation of boundary layer, kinetic energy will be lost. So kinetic energy here will be greater than kinetic energy over here. To make it equal, we have to shift this plate. So we have shifted this plate by distance of delta double star. Now over the fluid will not flow from this region, and fluid flow will be from this region only, and due to that what will happen, we will get kinetic energy in this case and in this case will be same. Then reduction in kinetic energy we have to calculate, means the mass flowing through this section multiplied by velocity, that we have to calculate. That will be the loss of kinetic energy due to lifting of a plate. So kinetic energy of fluid per unit time through the energy thickness will be 1/2 mass per unit time through delta double star multiplied by velocity square. So as I said previously, rho b delta double star, which is the height, this is the width, this is the velocity multiplied by u square, that is total velocity. So 1/2 rho b delta double star u cube is the fifth equation. Now fourth equation and fifth equation are giving us the same thing. Here is the total reduction in the kinetic energy due to boundary layer. This is the reduction in kinetic energy due to shifting of a plate. So equating equation 4 and 5, we will get this big equation. Let's simplify this, cancelling the common terms, and we will get delta double star is equal to 0 to delta small u by capital U into bracket 1 minus u square upon capital U square dy. This will be the final equation. With this, we have completed three types of boundary layer thicknesses: displacement thickness, momentum thickness, and energy thickness. Hope you have understood these things. Whatever doubts we will discuss later. In the next point, we will see the boundary layer separation. Thank you.